very much for the invitation to be here and to speak. This is a conference on categorical symmetries, and I think we all agree that the field made lots of progress and has lots of activities, not only a number of conferences this year, also this is impressive. I want to tell you something about CFT correlators. I think you can argue that the first instances where categorical symmetries have been discovered in the framework of rational CFTs. So we saw more than 20 years ago that you can implement symmetries by invertible defects. Well, in 2 dimensions, they are 1-dimensional. You can implement dualities, and all this was done for rational CFTs. This had the advantage that we could use 3-dimensional TFT. 3-dimensional TFT, as we now understand much better, at least if you use them on standard cobordisms, needs semi-simplicity. Semi-simplicity in CFT is not natural. So the state of affairs is very satisfactory for the rational case. It is not for general CFTs, and it is not for CFTs where people made lots of progress. So, for example, critical percolation, which earned a couple of field medals, is still beyond reach of algebraic methods. This is very unsatisfactory. So here I want to present to you a different approach to CFT correlators. It is based on scheme-theoretic methods, on string-net methods, Levin-Vance string-nets. It will incorporate also categorical symmetries in a way which I find interesting and which I want to explain in this talk. So actually, a lot in the talk will be secretly, maybe not semi-simple, but relatively semi-simple in a precise way you're going to see, but things are set up in a way that they generalize. Okay. Now I'm trying to. It's not working again. It's not working. Can I use here this, or is this disconnected? This is not connected. Okay, then yeah. Oh.
First troubleshooting on the one.
Can you try again? You can try. Okay. Could I point in a specific direction? No, you're still on the other one. Yeah. Okay, good. Do the old-fashioned way when people were using projectors, really, where an assistant had to sit there and they would. Well, there's a That's for the very old guy, like Alberto and me. Right now.
Right now?
Yes, it works. So I want to briefly put CFT correlators into context. Then I want to develop something which is unsurprising maybe for experts, but which needs to be developed in very concrete terms, a graphical calculus for pivotal bicategories. What is the important point there, which I will explain? Well, the important point is that we will look on how the graphical calculus depends on the categories I use as input data. And it turns out that in this context, Frobenius monoidal functors play an important role. So I will explain this covariance of this graphical calculus. I will develop briefly the string-net calculus, and then I will show how 2 different string-net calculi control relations between correlators and symmetries. And this is then the categorical symmetry part of the talk. Okay, not everybody here is an expert in 2-dimensional conformal field theory, so let me give you a sketch to get into the subject. Well, 2D CFTs have an infinite dimensional algebra of local symmetries. Vertex algebras say, I'm not going to tell you what a vertex algebra is. You need to know that it has a representation category which has certain structure, which I will specify on the next transparency, and that you can construct conformal blocks. So this is a system of vector bundles, a modular space of complex curves with marked points. consider them as solutions of chiral-Ward identities if you have a physics background. Actually, since these are solutions of differential equations, they are multi-valued. And since they come with a projectively flat connection, they give rise to projective representations of mapping class groups, and they obey factorization. And from this, one has to construct what really full local CFT is. The full local CFT, that's, for example, what you consider as the world sheet theory of strings, or what you would like to consider to describe universality classes of critical systems in 2 dimensions. So I consider them as consistent systems of correlators, something to be defined. And we will have several tasks to do. What I want to point out here already is that they are defined for a different geometry. They are defined for conformal surfaces. Well, they might have an orientation. They're actually different flavors of CFTs, while the chiral CFT is defined on complex curves. And we want to find then specific elements in these vector spaces of conformal blocks. Now, the fact that such questions factorize into different steps which are mathematically rather different, that's well known in mathematics. If you, for example, the character theory of reductive groups, then you first derive a differential equation, Harsh-Chandra equation, and then you have to say, this is in principle complex calculus, and then you have to find, using, for example, geometric representation theory, specific elements which are actually the characters. Mathematically, these 2 steps are quite different, and I will start the second step based on certain nice categories. So here, from vertex algebra, whatever it is, we get a category of representations. Specifying the category of representations is non-trivial. It's as non-trivial as specifying nice categories of representations of Lie algebras. This is known that we have to be careful here, but that's for the experts in this field. In nice cases, this is a modular fusion category. Well, what is this? This is a K-linear semi-simple abelian category. We are eager to draw the fusion, and we are eager to draw hence the semi-simple. And this is, in a sense, preparatory work for this. Rational CFT comes with, or a modular category, even if it is non-semi-simple, it comes with a lot of additional structure, a tensor form, a non-degenerate grading, and it comes with rigid duals. Rigid duals is something you require, but that's not natural from the representation theory of vertex algebras. Vertex algebras have a weaker notion of rigidity, so-called quotient of bed dualities. So Lucas knows about this and has done in work which will be very important for CFT in the future. Now, we have to somehow deal with these conformal blocks. And what we really have to deal with is the monotonies of the conformal blocks. They are multi-valued solutions of differential equations. So we just keep their monotony, and we want to get single-valued solutions with certain additional properties. So to this end, we use the following thing. We use an open-closed modular functor, and we will construct examples in this talk. So what is an open-closed modular functor? Well, it is formulated in a bicategorical setting. So we have a bicategory, a 3-layered structure of geometric data, a Bordism category. We take it to be oriented. There could be unoriented CFT. It's not the topic of this talk. And it takes values in an algebraic category. It turns out to be convenient to take profunctors which are also called bimodules by certain people. In our setting, this is not directly visible in the talk. Well, what are the objects? Well, we take intervals and circles and finite disjoint unions, and of course we have a monoidal unit, the empty set. Then the one morphisms are surfaces with boundaries, and for the 2 morphisms we take homeomorphisms up to homotopy relative to the parametrized boundaries. And the objects here, they are k-linear categories. Then here, pro functors are actually functors. A pro functor from A to B is a functor from A of times B to vect. And we take natural transformations of pro functors. Well, so for example, to this surface, what would a modular functor assign? Well, here we have two ingoing intervals, one outgoing circle. So we get something from the category, the pro functor, this modular functor assigns to the interval. This will be, in our case, C, the category that describes the chiral data itself, times C, and it goes to what this functor assigns to the circle. That's something to be computed, but let me tell you, it will be the Drinfeld center. Good. So this briefly sketches how the modular functor should take the representations of the mapping class group. Maybe I should say this here. So here on the top level, we had homomorphisms up to something. So, and we get here natural transformations. These are the representations of the mapping class group, a factorial system of such representations. Well, now our worksheet, well, let's look at this example again. We take a very general case because we are interested in categorical symmetries. So you see here a boundary interval, and you see here two boundary circles. Then the CFT can be in different phases. Here one is indicated in blue, the other one in green. Then there will be defects separating these different phases. There will be boundary conditions, and there can be point-like insertions. And so for a fixed modular category, what are these decoration data? That's established for quite a while. Here I say the phases are described by special symmetric Frobenius algebras, and the experts will realize this is the point where I insert some relative semi-simplicity in the term separable. The category itself doesn't have to be semi-simple. You'll see why at the moment this special symmetric Frobenius algebra is quite important for what we are going to do. Okay, so then here such a line defect, like for example the blue line, is labeled by a bimodule. It's clear bimodule over the algebra that's adjacent to the left and to the right, and the point defects are labeled by bimodule morphisms.
Where's the separable?
The special has encodes two things. It encodes that the co-unit is evaluated, or the unit is a non-zero scalar, and that the co-product is a one-sided inverse to the product. And yes. Thanks for asking. So now we also have some knowledge from years of studies what we expect for the field objects. Well, if I'm interested in fields on the boundary, and notice that here on the boundary things can be a bit more general. So I do not only have boundary conditions and the insertion changes the boundary condition, but there could be a defect ending or emanating from this interval. Boundary fields have one chirality, so they should be described by objects in C, and they will be described by inner horns. So that's a very compact and natural description, which we will recover by string net methods. The circle, well, this will be bulk fields. Here I'm writing the Drinfeld center. People with a physics backgrounds will have things like combining left movers and right movers in mind. But it is the following holds that the non-degeneracy of the braiding implies that the Drinfeld center is braided equivalent to the modular category in the modular category with the reversed braiding. So
Can you raise the board a little bit?
yes. So this here is the non-degeneracy condition, that this is really a braided equivalence. So that's why we use for this description, well, not only of bulk fields, but also of defect fields, why we use the Trinfeld center, which is much more natural and friendly to scheme theoretic methods. And I'm going to explain how precisely objects of this type will come out. So you see boundary conditions will be described by objects in the module category. And for a module category, you have in a home. Defects will be described types by module functors, which I'm here representing as tensoring by modules.
The C is a fusion category or not?
Not necessarily.
So what does it
It is a modular category by which you understand a finite tensor category, the tensor of the alpha together with a braiding, and this non-degeneracy regrading, non-degeneracy condition on the braiding plus the twist.
The condition is what?
The condition is that if I take C with its braiding and C with the reverse braiding, because once you have a braiding, you have also the opposite braiding, right? So you take the product of these two tensor categories, and there is a natural functor, since you are asking me to explain this, right? Because you have a natural functor from C into the Trinfeld center, because this object comes with its half braided. This is a monoidal functor. It's even a braided functor.
Why is C braided? C is braided itself.
C describes the chiral data of a CFT, and it has a braiding. And it doesn't just have any braiding, but it has a braiding which has a non-degeneracy. And this non-degeneracy condition can be phrased in different ways. We can say that in the rational case, the S matrix is invertible. That's it turns out that even without non-semi-simplicity, a non-degeneracy condition that's equivalent to several other good non-degeneracy conditions is this braided equivalence. Hence, I'm describing bulk fields, defect fields in the Trinfeld center, and not in terms of left movers and right movers, but there is a canonical such braided equivalence.
Yeah. Do you assume some finiteness on C?
Sorry, some?
Finiteness?
Yes. At least at the moment, this is rather a statement about our technical toolbox and the framework where we have many tools at our disposal than a matter of principle. And extending this is an important trend. There are recently papers, for example, you would like to extend this to the case where the category describing boundary conditions is a pivotal tensor category. There are recently investigations of pivotal tensor categories in the larger setting, where you have to work with partially defined Serre functors. This technology which basically. Any more questions? Good. So what do we have to do? Well, if we take such a worldsheet with all its decorations that will be described, denoted by this curly S, then we want to define a correlator. It's built from conformal blocks. So it should be an element in the space, the modular functor based on this modular tensor category. That gives us for the surface underlying S and the boundary values which I can read out here. And there are two conditions. There is compatibility with Sewing, which I will formulate, and there is invariance under the action of the lattice group. In particular, if you go to the torus, incorporates modular invariance. And actually, this here looks innocent. It is not, because our defects are topological. So if you move them a bit, this doesn't have any observable effect. So what is our mapping class group? Should it keep the defects literally fixed, point by point fixed up to homotopy? We wanted to answer this question, and it led us actually into these investigations. And I will give you an answer which has surprised us. And here, this mapping for the moment, let's take this naive here is fixing everything where I decorated really point by point. Later, this will be wrong, yeah, or it will be too restricted. Good. Now, let me work a bit. I like to develop a graphical calculus for bicategories. And this is the input for a modular functor. And the small thing you should keep in mind, which relates this chapter and the next chapter, is that stringnet modular functors are globalized versions of graphical calculus. And this is not a new slope. But let me start with graphical calculus. So we will set it up in a bicategorical setting. And we don't do this because we feel fun in moving one categorical dimension up, but we really need to do it because we have bicategorical data. We are labeling surfaces, or patches, we are labeling lines, and we are labeling points. Yeah, so 3-layered structure. So the bicategories in this talk will be k-linear, and they have horizontal compositions and units. And I'm not going to introduce bicategories axiomatically, but I want to show you these two diagrams. So you have objects, you have one morphisms between these objects, and you have two morphisms between these objects. Probably most of you have seen such a diagram. For us, the Poincaré dual is much more convenient. So you see, I'm taking here now, I'm reading such diagrams always from below to above. And then I will have objects assigned to patches in the surface. I will have one morphisms assigned to lines, and here alpha, beta, gamma are two morphisms. And these string diagrams in the first step, they are two-framed and progressive. What is progressive? Well, these lines have always to move up. They cannot wiggle around for the moment. This will change. And they are two-framed in the sense that if I want to evaluate this direction and the other direction are different, and we have to get rid of this as well. So actually this, sorry, let me go back. This direction here will be evaluated by taking tensor products, or rather horizontal composition. This will be vertical composition. Now, there's an important notion which generalizes from the bicategory of categories. That's the notion of an adjoint morphism. So two one morphisms are adjoint if the adjunction is exhibited by evaluations and co-evaluations. That's like rigid dualities, and they have to satisfy zigzag relations. And we will also use the standard notation for dualities. Now, what is a pivotal structure? A pivotal structure on a bicategory where we fix left and right duals. Having left and right duals is a property, not a structure, but fixing them up to isomorphism is something we have now done. Well, it's an identity component pseudo-natural transformation, which allows us to identify the bidual of one. That's the identification of biduals, and that's a finiteness property. As you know, the bidual of a vector space is isomorphic to the vector space. The vector space is finite dimensional. And we will assume that this is strictly pivotal in the sense that this identification is the identity, and I'm not going to discuss strictification results in this talk, but there are. So what is the consequence? Left and right dual are equal, so the evaluation of these two diagrams is the same. Now, what are examples for input data, and what are the examples I'm going to use in this talk? Well, the first thing is any monoidal category is bicategory. Now, we can take a monoidal category, for example, the category of chiral data. Of course, we forget the braiding then, but for our purposes, a lot of information of the braiding here still survives the Trinfeld center. That's the point why this approach works. And then we take the bicategory with one object, where the monoidal endomorphism category of the single object is just our C. And the second bicategory are these Frobenius algebras. You should think about them as the data that label. Yeah, so this is the chiral level of a CFT. These are the data that label defect types, 2 bicategories. And now what happens to the graphical calculus? Before it was framed, so x-axis, y-axis, and progressive, to be read from below to above and only going above. Now we drop progressive and we drop framed because we have good diagrams, good dualities. How do we do this? So really the pictures we are going to work with will look as follows. These coupons will become circles, and we will work on a disk as the standard canvas. This is a bit not so surprising if you describe a CFT, or if you do representation theory more generally. You look at invariant tensors. We have here invariant tensors with a cyclic invariance. And essentially Moore-Seiberg formalism was working with more terms of such invariant tensors. That's all, just to say it in a different language. Okay, so let's formulate this graphical calculus. This is the theoretic state of work of Costello as a symmetric monoidal functor, and you'll see why I do this. So I take the category of correlates, and I go to the category of vector spaces. Actually, this will be finite dimensional vector spaces. So what are these corollas? Well, you see, a corolla is simply a diagram of this type where I have colored these things by a bicategory. The bicategory can be chiral data or defect data. I take the 2 calculi, and you see here, these are the objects of the bicategory, the 1 morphisms, and in the center, I have a 2 morphisms. Well, then here, what are the morphisms? Well, we have here objects are actually disjoint unions of corollas. And you see here an object is given by such a diagram. Please note these 2 shaded gray circles. You see that the boundary value of this circle fits exactly what you have here. So for example, here you have these 2 purple things. So I can glue this in, and we will use this for evaluation. And the boundary of this circle is actually what you see on this corolla. So this is these are the morphisms, and composition is, so if you want to start here and compose with this here, you take this disk and you insert it, and that fits the boundary data. So this is a category which is quite natural. And we have to investigate it a bit. This is relatively simple combinatorics. Any morphism in this category of corollas can be decomposed into a finite disjoint union of morphisms of different type. And we do this little exercise, which is not interesting in itself, to distinguish a certain subcategory of corollas. Well, what do you see? You can compose, if there's a line between 2 of these gray shaded disks, which are incoming, that's what we call operatic composition. There can be partial traces that are to be taken, and then with horizontal products and whiskering. These are disconnected diagrams, and we consider a subcategory where we drop these morphisms, and we call this the category of connected products. Yeah, so this has the same object, but it has less morphisms. It has less morphisms because, for example, whiskering, although it looks simpler, behaves more complicated in the graphical calculus. This is, by the way, something that's known to people in linear logic, and that's why we were aware of this fact. So we want to set up this symmetric monoidal functor, which gives us a graphical calculus. So to this corolla, we have to associate a vector space. What do we do? Well, we take, we partition the points on the boundary into 2 sets by choosing an auxiliary point, say here and here. Then you see this here is in red. These 2 are in blues. In blue, then we consider this as ingoing and this is outgoing. And we take this space of morphisms in the bi-category of two morphisms? Well, and the bi-category means the vector spaces for the two. Now, then here we choose auxiliary data. You have to do an exercise. You have to show that the pivotal structure is enough to get rid of the auxiliary data, and it is enough. So, for example, if we have such a configuration and we choose it in different ways, we get vector spaces which are related by canonical isomorphisms, and formally we take then the limit of, since these are isomorphisms, the co-limit over these diagrams. Really, we take symmetric invariant. Yeah. And for a functor, we have to define it on morphisms. So this here, recall, this is a functor. We have here an ingoing, a morphism. We have here an ingoing disk. Here, ingoing disk. So the boundary values here are the ones of this corolla. The boundary values here are of this corolla, which goes to the outside. We choose this auxiliary data. We get, by choosing the auxiliary data, such a diagram. If we insert concrete morphisms here, we can evaluate this diagram, and you check it doesn't depend on the auxiliary data, and you get here functor, which really encodes the essence of graphical calculus. It's a graphical calculus on disks. So now, as I mentioned in the introduction, we have two bi-categories. They should be related, and we want to know how the graphical calculus is related. And the information on correlators is in this relation. And I think this is a very nice thing, because interesting mathematical information should be how things are related. So the index theorem is not about computing a number, but it is about how a morphism of, say, schemes affects other things. Yeah, so, okay, so we consider Lax functors. So if you have a bi-category, you definitely agree that I should be able to map objects, and I should have on home category, I should have a functor, and this functor should be compatible with horizontal composition. Now you might say first mapping and then composing should be the same as first composing and then mapping, and then you will put here as a filler an ISO. But we don't put an ISO. I do not require this to be an ISO. And similarly for the unit. Now, let's use a graphical notation. So here I'm first applying f to the functor capital F to small f and small g. And here I'm doing first the composition if I go this way. And then I apply f, and we have a natural transformation between it, which I depict in this way. And you see, it looks like quantification in graphical calculus. This is to suggest. Well, this has certain properties. So it has to be natural, but it should also be compatible with taking multiple compositions. So there has to be a lax associativity and a lax unity. And again, these are not ISOs, they go in one direction. Now, if you play this game in this direction, you can play it in the other direction. So there's a similar structure of an oblax natural transformation, where for lax transformation, we have this one. For an oblax transformation, we have this. So we do not require that the oblax transformation is the inverse of the lax transformation. Let me make a comment. Why is this natural? Well, if you introduce the tensor product, it is to investigate bilinear maps. These are maps from, say, V tensor W into something. And in a rigid category, we are using this also to describe maps from an object into several things. And it's not clear that one and the same tensor product should do the job. There could be different tensor products for ingoing and outgoing. This is a standard thing. This is more frequent than you think. And this is precisely what happens in quotient-Quartier categories. There are two different things. And if for people in logic, it's completely natural, because if you want to go from any composition of statements to another composition of statements, and we want to compose them somehow, then at your postulates you should be strong and require and at the output you should require or. And these are two monoidal structures, and they're definitely very different. So, for example, for one, it's the empty set, and for the other thing, the whole set, which is the monoidal unit. Yeah. So, but they are related by a negation, and this is all CFT counterparts which are not relevant in this context. So I just explained it why I'm not at all reluctant to have two different structures which are not inverses. But of course, they need to have some compatibility. And what I want to do is, if I'm given a natural transformation which appears in the graphical calculus for the by category B, I want to be able to turn this into a natural transformation in the category B prime. And you see, if I take the horizontal composition of one morphisms and I go to the horizontal composition here, that's what I can do by using here this structure here, but then I want to undo this horizontal composition, and I'm doing this with the oblax, with the lax structure here, and the oblax structure. That's what you see here. That looks like a product. This is the lax structure, the oblax structure. They are not inverses. Okay. So now the question is, well, I should have said we call this procedure the F conjugate of a natural transformation. Yeah. So this is also in particular mapping invariant tensors in the B world to invariant tensors in the B prime world. When does this preserve a graphical calculus? And now we can say what preserve means. Graphical calculus is a monoidal functor, and we know how to change here by F conjugation the corollas, and we want to have here an iso. Well, here on corollas, we take exactly what I described. And there is an optimal case which is irrelevant if our functor is rigid and preserves the co-units, so we preserve the dualities, and it is a pseudo functor, so the lax structure is the inverse of the oblax structure, then it preserves the graphical calculus, and that's not a deep theorem. That's easy to check. And again, this is not what we will need, but rather what we will need is the following notion. This is the functor is Frobenius. So Frobenius is actually a special case of what people in linear logic call linear functors. Linear functors don't have to do anything to do with vector spaces, so the terminology is confused. But they have been in the literature before, yeah? So it's not new to us. It's not new to us. And you have here this compatibility condition for the oblax and the lax structure. And everybody who has seen graphical calculus for Frobenius algebra feels hopefully a déjà vu. Good. And separability for this functor is what I didn't mention explicitly for an algebra. It is here that if I take here the lax structure, the oblax structure, this is the identity, but the other way around, it is not. Okay. And then you can prove, and I'm not going to prove this here in this talk, that such a rigid Frobenius functor preserves the connected part of graphical calculus. So it preserves operatic composition and partial traces, but not whiskering and the horizontal part. So we have to do something, and some interesting correction appears at this time. Okay. Why does it not preserve this? Well, if it would preserve, then if I take here two morphisms and I map them by F in two different ways, and I'm using here naturality to pull this down, then you see these two things should be equal, but this here, under our assumption of separability, this is a constraint datum of our functors. This is not an ISO, it is only an idempotent. And the fact that it's an idempotent is again one of the secret relative semi-simplicities about which, to be honest, I'm unhappy. Okay, so we need such a rigid separable Frobenius functor, and actually it is the functor which relates the defect decoration data, which had been Frobenius algebra, blah, blah, to the chiral data. That's a Frobenius separable, that's a rigid separable Frobenius functor. Functor is kind of obvious. What do I do to objects? Well, to objects, I map them to the single object here. I don't have much choice. To a bimodule, I map to the underlying object in the category, and a natural transformation, I map to the underlying natural transformation. And it comes, well, here, it comes with an actual Lax monoidal constraint. And I find here, and that's why separability is important. Well, for a tensor product, you have a natural structure morphism in this direction, but in the other direction, you would need a co-tensor product. I get it by splitting the idempotent. I can split the idempotent because of separability. That's why I'm using this. And then you see that I'm here. I can represent this idempotent. This is known to everybody who has worked a bit with separable Frobenius algebras, that the idempotent can be written as in terms of the unit and apply the co-product to the unit. Good. So we get these idempotents. So now we can do the stringnet models. This is standard, so I can be quicker here. We will apply it to the two bicategories, to defect data and to chiral data. Okay. So what do we do? We take an oriented surface. We fix boundary values. What is a boundary value? Well, to these intervals, we assign objects, for example, Frobenius algebra in one case, to the points 1 morphisms. And for fixed boundary value, we consider the vector space that's freely generated by labeled surfaces with this boundary condition. It's a huge vector space, not finite dimensional, not infinite dimensional, counterplete dimensional. It's really huge. And we mod out by local relations which are given by the graphical calculus. So if two of these surfaces, let me phrase it with two to make it simpler, are such that the evaluation on this disk and on this gray shaded disk give the same, I'm identifying things. Standard Levin-Band stringnet with the only modification that I now also have labels for the surfaces, which is natural since for defect for CFT phases I need a labels. Yeah. Okay. So the evaluation functor, that's an aside. Let me be rather quick on this aside. That should evaluate. This will be a functor from graphs to vector spaces. Well, this will be actually partially colored objects here. So I'm not coloring the one, I'm coloring the patches by objects, but I'm not the edges by one morphisms, but not the vertices. And the morphisms are given by evaluation. Well, then you can you define it. Sorry, I have to go back. So so you take for the surface, to the surface, you assign the tensor product of invariant tensors, and you get maps between the invariant graphical calculus. And then the stringnet space in co-limit. This is nice because I think one of the trends that we will see at future conferences is that you don't want to do just modular functors with values in vector spaces, but in chains of complexes of vector spaces, derived modular functors. And I'm sketching this to show that the formalism has been set up in a way that you can extend it. We will not do it today. What I should emphasize here is that the mapping class group acts on the surface. It acts geometrically, hence no central extension, as befits a modular functor or Trinfeld center. And there is factorization. So we have a modular. Okay, so we have our modular functor. So I should briefly discuss what happens to one manifolds. So to the one manifold, we have to assign a cylinder category. category, which I call the cylinder category. So the objects are boundary values. I've described what boundary values are. They are given in terms of objects and one morphisms, and the morphisms between them are stringlet spaces. This gives categories which are not abelian categories typically, but they don't have to be. Yeah? So now there's a little trick we have to use. It's the following. Our bicategories are pointed. So here, this is the category of chiral data. It has a single object, so a pointing a distinguished object is automatically there. And for the defect data, we have the trivial Frobenius algebra, so for CFT people, case. Yeah. Now, so what we do is if we have an interval, we will take this pointed object at the very end and then extend a little bit the interval. That's a technical point, but it's important. And then you can compute these categories, and there's a nice bonus now. So everything we do will be functorial under embedding of one manifold. So we actually get here, for example, an embedding of the category assigned to such a labeled interval into the corresponding circle. This is nice because now actually secretly we are switching our framework. Before, if we work with cobordisms, then the morphisms are manifolds with boundaries. We are neglecting embeddings, which are very essential for locality in field theory. So it's good to have two different types of one morphisms which are compatible. The natural framework for this is a double category. But I'm not going to talk about double categories today. And this functor is also nicely compatible with monoidal structures. And you see that after simplifying, so idempotent completion, but let's not go into this detail. So cylinder categories will be actually C and or for the interval or S1 for the for S1 the Trinfeld center. Well, that's in disguise the old planar algebra construction of Trinfeld centers. Yeah? So and you can compute explicitly what the geometric embedding induces. It must be a functor from C to Z of C. It turns out to be the left adjoint of the forgetful functor from the Trinfeld center. So something really natural in the theory. And also the stringlet space has to be massaged a bit to accommodate this idempotent completion. And the whole thing, if we add semi-simplicity, could be extended to a derived VO TFT, but we don't extend it, and we do not want to extend it. You can prove factorization, and let me say, this goes beyond semi-simplicity. You can show that the if you glue, then the functor that you get for the glued surface is, or the pro-functor, is actually a co-end of the functors you have before gluing. That's and that doesn't require any semi-simplicity. It requires, however, in the present formulation, double point. It's not working with weaker notions of rigidity.
Did you say semi-simplicity, but not spherical?
Sorry.
You're not assuming any spherical condition.
We are working here in the pivotal categories, right? Yeah. We don't have spherical, and we do not evaluate those figures. That's a very big thing. Okay, so now let's finally go back to CFTs, and let's go back for simplicity to rational CFTs. And I want to explain to you what we understand by a universal correlate. Okay. So we start with this worksheet, which has the decoration data in one of these bicategories we discussed, and for which we have constructed the stringlet model or modular functor. So take this worksheet and then do this little technical thing. We add here for the boundary condition, we add here this little half disks, which we label by the distinguished object in our categories, which have a distinguished object, which are marked categories. well, essentially it means that we can describe a left module also in terms of bimodules, meaning a left module as an A, monoidal unit bimodule. It's not a big deal. And then we map it to here, the following thing. We take the same configuration, take these blue and red colored things, and we replace them by a network which is labeled by these Frobenius algebras. The network has to be sufficiently fine, but you know Frobenius algebras in labeling is nicely compatible. So this is a way to get rid of these things which morally should be defects, surface defects in some TFT, but which we cannot deal in the full generality without semi-simplicity in this way. So we add this here, and the vertices are morphisms. That's where we do this conjugation using the Frobenius functor structure. So what we now do, for example, is if we consider a boundary field, well, then what we do at the boundary is we take the labels in the second stringlet calculus, and we add here these projectors. I've drawn the projectors simply as lines, and you see this projects a tensor product of M and N to a tensor product over A, but that's a way to represent the inner home, and which you can do in the set of the context. Okay, and for the defect fields, we do the similar thing. So to such a circle, we also add projectors for all segments of the disk. And you can check, this is a technical word, which I'm not going to present here, that this gives a very natural quantity. Actually, you can describe it by observing that here we were using module categories over C. You know that module functors are module categories over the Trinfeld center, so you can look at inner homes, and these inner homes are the natural objects to describe fields in the CFT. And if you compute what they are, you get formulae that are around in the literature for 20 years, but it's more compact, nice to handle, and this gives the same spaces in stringlet realization. In particular, the bulk fields are given by this, well, it's probably decent to call a home in a category of functors internal natural transformation. So bulk fields are given by the internal natural transformations. This was what people called the full center. You know that if I would drop the net, then you get natural transformations of the identity functor. That's the center of an algebra. Yeah? So makes a lot of sense. Okay, so we take the worksheet, we map it to this here, and this gives us, this configuration gives us a class in, or the class of this configuration gives us a vector in the stringlet space for the stringlet constructions based on the defects. Here gave it the poetic name to call this vector the quantum worksheet, first of all, because quantum doesn't need any justification anymore these days, but it will get a justification in a moment, right? So you see that different things here can give the same vector, because if there are relations among defects which are encoded in the graphical calculus, they will give the same vector here, because this is a vector space of diagrams for graphical calculus. So it's not, you cannot reconstruct from this quantum worksheet to complete worksheet. Yeah? And we show that actually the correlator only depends on the stars. This incorporates all kinds of relations you have between correlators. Of course, you all know many of these relations. So for example, if you have invertible that you can replace this by something like this. And you could derive it here by doing a graphical calculus and noting that inside the disk they evaluate to the same thing. Yeah. So, but this here really captures all relations, not just the ones based on invertible things, or yeah, it really captures all the relations of all the correlations. And so really the correlator which is a vector here. It factors via a map here, and this map, which relates these two stringlet calculi, which is built from this Frobenius monoidal functor, it is really capturing the correlators. And since it can be obtained as a pullback, the word universal is not in the sense of a universal property I want to formulate, but in the senses you can obtain bundles by pullback from the universal. Yeah? So, two remarks. This construction of this universal correlator, it uses that this functor which goes from defect data to chiral data is a rigid separable Frobenius functor. And these Frobenius networks we added here, they exactly compensate the failure of the graphical calculus to preserve whiskering in horizontal fields. So that's what we use here. And so let me say it again. So the CFT cannot detect the complete worldsheet of the geometry. So it can only detect the vector in here. So, and what it can detect is determined by defect. I claim independently on all the mathematical tools we developed here, and which I spent also quite some time to talk about. This is really an important role of defect data we should keep in mind. The stringlet spaces built from defect data, they capture relations between correlators, and they give us some indication what's measurable in terms of correlators. Okay. Quick remark on the mapping class group. Look, if I have an invertible defect, then I have this relation. So these two configurations, if the defect is invertible, they give the same correlator, same value. So I cannot distinguish them. If you look at this naively from the mapping class group, one will have a Dane twist, the other will not have a Dane twist, right? You can turn it around here. This will not have an effect here or not. So how do you now define the mapping class group? Well, is the Dane twist in the mapping class group or not? Well, the geometric mapping class group acts on the stringlet space built from data. And if I now take the vector that corresponds to the worldsheet, I can consider its stabilizer. And that's what I define as the mapping class group. And then this correlator in this is invariant also under the Dane twist in the sense. So you see, you needed to know what is the mapping class group. So the Dane twists are in this correctly defined mapping class group, and that was actually the starting point of this project, which took us a bit further away in the end. So here, so what is the message? Well, it's clear in our setup. We have the borders and categories. We have two modular functors, one built on defect data, one built on chiral data, and the correlator gives us actually something which fits into a pseudo-natural transformation. Pseudo-natural transformation has two things, so it unifies even the universal correlator and this obscure thing, which I didn't give a natural mathematical name, or field data. And you can upgrade this whole thing to symmetric monoidal double categories to get also locality in the field theoretic sense of embedding manifolds into the game. And that's something that's about to be written up. And I want to conclude with a summary and an outlook. So stringlet constructions are a very natural and convenient conceptual home for CFT constructions. They don't force us to go to 3 dimensions. This has an advantage that the mental gymnastics in 3 dimensions is very exhausting, at least for me. We just do 2-dimensional geometry, and we don't need strong simplicity requirements to construct something completely on 3 manifolds. The bicategorical stringlet construction captures symmetries and the observable part of the worldsheet, and it keeps systematically track of relations between the CFT correlators. So, and again, my hope is, of course, that what we see in CFTs, 2-dimensional CFTs in the well-defined setting, will be recognized in variations and generalizations in other settings. Outlook, well, we have to fully go beyond semi-simplicity. What's much more subtle is to go beyond rigidity, because interesting problems like percolations do not have rigid chiral data, but the work of Lukas Müller and Lukas Schweigert on modular functors in this setting will be quite important. Also, you're not using stringnet or scheme theoretic methods, but there should be something. It's interesting to go with these constructions to go to homotopical versions, and this will have applications, at least in mathematical physics. And with a lot of progress being made at the moment in higher dimensional CFTs, higher dimensional things. But these are all future directions. Thank you very much for your attention.
So there are more questions?
When you define the string net space, it was a co-limit over labeled graphs, quotient by local relations. Could you say a word if and why any of those terms are finite dimensional? Does that make sense?
Yes. First of all, it makes sense to ask about finite dimensionality if you use in your scheme theoretic input data finiteness conditions, right? Like, for example, finitely many simple objects, finite dimensional Hom spaces. And then the way the simplest argument I would see is you can simplify the graph a lot. And if you explain to somebody what a Riemann surface is, you will draw almost immediately very simple graphs to explain what a fundamental group is. So you show that the local relations allow you to go to such a setting, and then you investigate what you need there. Then you need essentially to label specific corollars where things come back. You have to show that these spaces are finite dimensional and that you have a quotient of this. That's very roughly the sketch of this.
So that shows that the values of the functor you're taking the co-limit of are finite dimensional.
Yes.
And the string net space
The string net space is this functor evaluated for specific boundary values. Because a linear functor, if I evaluate it for a specific object, it is described in terms of a vector space. Since we work with pro-functors, it is literally a vector space.
More questions?
In the special case of coordinate algebras in the category of vector spaces, does this reduce to the defect equality?
If you take the bond category. Well, if you it reduces if you do this with vector spaces, it reduces to a two-dimensional defect TQFT. Yeah.
Yeah. Questions online?
I wanted to ask about the correlators that detect only basically the defect. What is left over in the defect picture. So if one would define an observable as something correlators can detect, is then the statement that all observables are somehow given by defects? And is there also from the physics, is this natural?
Well, this is an interesting question. Let me point to one thing to make the answer. So this is the text diagram you implicitly referred to, right? And what I see here is essentially that this arrow factors. So I've explained what I cannot detect. We have a suspicion that this arrow is, at least in the setting where we are working, it is an isomorphism. It's not completely proven. It is an isomorphism roughly, very, very roughly, just to give you the idea, for the same reason as any morphism between Frobenius algebras is an isomorphism, and the Frobenius monoidal functors are not that far away from Frobenius algebras that we even hope that this argument is. And if I prove that this is isomorphism, I have an affirmative answer to your statement. But you see, where the mathematics for this question sits, what's natural to physics. Well, I think there are definitely people who have strong physical approach to the subject, and maybe this is a point for this study.
I think we should stop here. Great. Thanks, Christoph again.